Okay, so time for examples. As a first example, let's simply take our good old r to the n. N is a natural number, could be 1, then would be just the real numbers, and we know that this is a vector space. We know how to add vectors. So little x looks like this. It has components x1 until xn, which are all real numbers, and we have the usual addition, we have the usual multiplication by scalars, and so on. And now let's look at the usual norm in there, which is the following. So the norm of this same vector x shall be defined as the square root of modulus first component squared plus and so on modulus last component squared. You would call this the Euclidean norm, named after Euclid or Euclid. Euclidean norm. And of course, you should only do so after you've checked that it really is a norm. So you have to check properties 1, 2, 3. Yep, let's do that. Okay, well, maybe one more word for motivation. We know this norm for dimension n equals 2 and 3, and there we can easily understand it by the Pythagoras theorem. Then you just extend it to other n's and make sure it still is a norm. So first property would have to check that this equals 0 if and only if your vector equals 0, and by what we just checked here in our remark number 5, we don't even have to check the other direction, right? So we only have to check that norm equals 0 implies that it is the 0 element. Okay, so if the norm is equal to 0, then let me just paint this in here. Then that would be equal to 0, which means that the term underneath the root would be equal to 0, but then however each one of these terms is greater than or equal to 0. And if the sum of these is 0, then every one of them has to be 0, because as soon as one of them is positive, there's no negative behind them that could compensate for that. So they all got to be 0, which means x1 is 0 up until xn is 0, which means your vector is the 0 vector. Okay, property 1, check. Property 2, the norm of alpha times x. Okay, so there's a little alpha coming as a factor in front of every component, x1 to xn, so your norm would just be computed as follows. So it's the root of alpha times x1 modulus squared plus and so on alpha times xn modulus squared. Now for each of these you just, modulus of a product is the product of the moduli, so this is okay, and so on, right? And then you can get modulus alpha squared out under the root, so you have modulus alpha squared, and then you're left with modulus x1 squared plus and so on modulus xn squared. And then the last thing you have to do is just to get this modulus alpha squared out of the root as a modulus alpha, and there's your result. Okay, so also property 2, check. Property 3 is the triangle inequality, so the norm of x plus y less than or equal to norm x plus norm y is again a bit tricky, and again, let's postpone that. I promise we're going to get to that at some point, but not now. Postponed. But of course, it will turn out to be true, and then we can call this Euclidean norm. You may have wondered why I was putting modulus signs here, because, I mean, the square makes it positive anyway. I have two answers for you. The first answer is because then I don't have to change anything if I replace Rn by Cn here, but for Cn you need the modulus signs. The second answer I can give you is the following. We have one other direction of generalization, where instead of taking squares here, we take, let me say, pth powers, and to compensate for that we take the pth root, and we do this for number p which is greater than or equal to 1. You do not call this the Euclidean norm anymore, you call it the p norm, what you get then. So the Euclidean norm is what you get for p equals 2. But you can see that all the proofs here carry through as they did before. So here's a pth power, but then after the pth root it's again away, it's gone. Right, so we call this the p norm, and p is got to be greater than or equal to 1. You often write the little p down here also, so we can all see it's the p norm and what the value of p is. So the Euclidean norm is just the 2 norm. Alright. Again, from here there are different directions to go. Let's start with the first direction, where we say what happens to the p norm if p goes to infinity. So let p go to infinity, which is allowed. Is there a limit? And yes, if yes, what is it? Let's try this for let's try this for one vector. Let me say just a 2D vector where we have I don't know, 3 and -2 as the entries. Then what is the p norm? Well, the p norm of x is just the pth root of 3 to the power p plus -2 to the power p. And to see where this is going as p goes to infinity, you, well, first of all, give it a little thought. Right. And of course you have to put modulus signs here and here. So let me simplify again. So this is pth root of 3 to the power p plus 2 to the power p. Now obviously 3 to the power p is growing faster than 2 to the power p. So this probably dominates this term, and then you take the pth root. So the result might be 3. Let's check for that. Let's see whether or not that is true. So I would rewrite this as 3 to the power p, and then in brackets you get 1 plus 2 to the power p divided by 3 to the power p, or I could say 2/3 to the power p. Okay, is underneath the pth root. Now this 2/3 term here is between 0 and 1. And that's because we are dividing the smaller one here by the larger one there. So we are factoring the largest of all out to the left. It would be just too easy to argue that as p goes to infinity, this term goes to 0, so we don't have to consider it anymore, and there you are, 3 to the power p. Pth root gives you 3. You cannot do that because you cannot take the limit at different points at different times, right? So you cannot send this p to infinity before you send that p to infinity also. So they have to do that at the same time. So it's not quite as easy as that. Well, let's write it down again. So we have pth root 3 to the power p, and then there is 1 plus 2/3 to the power p. Now obviously this 3 to the power p, let me just mark the 3, comes out of this, and we have it in front. So what remains under the root is 1 plus something, and the something goes to 0. How about that argument? We could say that this term is between 1 and 2, okay? No matter what the value of p is, it's always greater than or equal to 1, but always less than or equal to 2. So as a consequence, so we have 3 times pth root of 1 plus 2/3 of p. So the whole thing here is between the pth root of 1 and the pth root of 2. Okay, now you can see where this is going. The pth root of 1 is always 1, and the pth root of 2 is not always 1, it's convergent to 1. You did that in your analysis course. Okay, and now we're there. So you can squeeze this expression between 1 and something that goes to 1. So the whole thing must go to 1. And there is this 3 in front, so this converges to 3. So indeed, our gut feeling was right. You just take the maximum here, and that will win the race. So in general, we get that the pth norm of a vector x1, xn converges as p goes to infinity to the largest of the moduli of x1 until modulus xn. And that expression, however, will be given the following shorthand. We just call that the infinity norm of our same vector x. So this is a definition now in that direction. And the name infinity norm is obvious where it's coming from. It's the limit of the p norm as p goes to infinity. Again, this is a norm. You could assume so because it's the limit of a sequence of norms, but that is not a proof. So again, you have to prove that this is subject to 1, 2 and 3 of our definition, and 1 is quite easy because this is, well, this maximum is 0 if and only if each one of these is 0, which means the vector is 0. Okay, if you multiply by a little alpha, then you get alphas in here, and then modulus alpha comes out of the whole thing. So also this is simple. And the triangle inequality is not as complicated as it is for p less than infinity. You could try it out yourself. Sure, you'll succeed to show that. So this is not so difficult here. So in the end, what we often do is we speak of the infinity norm, and we allow p to be in this range. It looks a bit odd if you see it for the first time, but we are also allowing p equals infinity, in which case we are talking about that norm that we defined here. Now, the best way to get a geometrical understanding of these p norms, including the cases p equals 1 and p equals infinity, is to take the dimension equal to 2, so you go to R2 and you look at the so-called unit circles. So the unit circles are in R2 with the p norm will look like this. Well, you're interested in the set of all vectors x1, x2 of R2, where the p norm equals 1. So let's try to draw this here. So here's your x1 axis, x2 axis, and the points that will always part of the unit circle are points like this one, where this is just point 1, because this is just the vector 1, 0, and whatever powers p you take, 1 to the power p plus 0 to the power p will always be 1, and then the root is still 1, so this is on the unit circle. And so similarly also that point will always be on the unit circle, but also this one and that one at -1 will be on the unit circle, because we are taking modulus signs before we take powers. Okay, I mean the most common form of unit circle is, let me try to get this right, kind of, it's our usual circle, and this is what you get when you plug in p equals 2. I mean, this is your Pythagoras distance, Euclidean distance way to measure the radius. But what else do you get? For example, if you take p equal to 1, let's try for that. So if you take p equal to 1, then your 1 norm, which has to be 1, so 1 shall be the 1 norm of x, which is then modulus of x1 plus modulus of x2, both of them to the power of 1, and then take the first root, which doesn't affect anything. So this is your expression, and it's easy to find that the graph looks like this. So in the first quadrant, where x1 and x2 are both positive, you can just drop the modulus signs and get this straight line. While in all the other quadrants, one or both of the modulus signs are in action and they flip things around a little bit, so that by flipping and flipping you're getting this sequence of lines which just results in a square. So the green thing is a square, it's standing not quite upright, it's standing on one of its corners, and that's your unit circle, as funny as it sounds, for p equals 1. Now if you increase p, you will find your circle to get larger and larger. Let me draw. Maybe this is what you get when you take p equal to 10 or so. Of course I'm making this up now, but this is what you would observe if you did the numerical computations. Oh, let me write p equals 10 here. Okay, and the fact that the infinity norm is just the limit of the p norms as p goes to infinity gives us already an idea of what the unit circle in the infinity norm will look like, but let's do the computations ourselves. So what is the infinity norm? So for p equal to infinity, the norm that has to be 1 is this. So it's the maximum of modulus first component and modulus second component. Well, of course, this point here, 1, 0, is subject to that condition. You're still subject to that condition if you change your vector a little bit. If you put 1 here and maybe 0.1 down here, then still the maximum is equal to 1. So what I'm saying is you're just walking up vertically a little bit, and then this works up until you go to 0.99 something, and then it would still be fine, just about, if you took the second component to be equal to 1, and that's where it ends, right? So you can walk up in vertical direction up until you end at that point. Okay, and then just by modulus and symmetry arguments, you can see that your unit circle, in the case p equals infinity, is in fact this square, which is now standing on one of its sides, but it still contains the 4 points that I was marking at the very beginning. In one of the exercise problems, I'm asking you what would happen if we allowed p to be less than 1, so something between 0 and 1, let's say a half or so. From this drawing, you could already imagine that for p less than 1, you would probably get a graph like this. Okay, and then you would have to argue why this is not good. But this is part of the exercise sheet, so you should look at this, and then we can talk on Monday evening.